Hello friends, in the last lecture we have studied fundamental theorem on homomorphism of groups. Now we shall consider the next result as a lemma. This is lemma number 17. Let phi be a homomorphism of G onto G bar with kernel K, or H bar a subgroup of G bar. Let H be defined by H is equal to X belongs to G, those elements of G, such that phi of X belongs to H bar. This is the definition of H. Then we have to prove that H is subgroup of G and H contains K, kernel. If H bar is normal in G bar, then H is normal in G. So this also we have to prove. And furthermore, this association sets up a one-to-one mapping from the set of all subgroups of G bar onto the set of all subgroups of G which contain K. So this is what we have to prove. Now we shall prove the result. See here, what is given is phi is homomorphism between two groups G onto G bar. Suppose this is G, group G, and let us suppose this is G bar. And phi is a homomorphism. Further, H bar is subgroup of G bar, that is given. So H bar is subset of G bar and it's a subgroup. And corresponding to this H bar, we have given H defined as those elements of G whose image is in H bar. So that means this will be H. And if X is in H, its image is in H bar. So that is by definition we have given. X belongs to G such that phi of X belongs to H bar is the set of H. And now we have to prove H is subgroup of G and that contains the kernel K. Further, if H bar is normal in G bar, then H is also normal in G. That we have to prove. Now we shall consider the proof for H is subgroup of G. And first we shall show H contains K. We shall prove that H contains K and H is a subgroup of G. To prove H contains K, suppose K is in K. K belongs to K, an element in kernel. And by definition of kernel, the image of every element in kernel is identity of G bar. So therefore, if K belongs to K, this implies phi of K is equal to E bar. And you see phi of K is E bar, so that means E bar is H bar is subgroup of G bar, therefore E bar is in H bar. So this implies phi of K belongs to H bar since H bar is subgroup. So it must contain the identity. And if phi K belongs to H bar, by definition of H, you see, if pi X belongs to H bar, then X belongs to H. So therefore this implies K belongs to H. Because its phi image is in H bar. If phi image is in H bar, then the element belongs to H. So the inverse image is in H. And thus this K is in H. And thus if K is in K, then that implies K is in H, means this K is subset of H. So therefore K is subset of H, or H contains K. And also H is non-empty. And H is non-empty because K is the element in H. Now to prove subgroup, see further we have to prove two more properties by the lemma on subgroup. That means H is closed and H contains inverse for every element, and we now consider H is closed or closure property. For that purpose we shall consider two elements in H and we shall show their product is also in H. Let X and Y belongs to H, two elements in H. So if these are the elements in H, see the definition of H, then their images must be in H bar. So that means phi of X and phi of Y both belongs to H bar. So this implies phi of X and phi of X belongs to H bar and phi of Y also belongs to H bar. Now because H bar is subgroup, it is given H bar is subgroup of G bar, H bar is closed, and that means these two elements are in H bar, their product must be also in H bar. So this implies phi X into phi Y belongs to H bar. Reason for this is since H bar is subgroup of G bar. Given, this is given. Again, phi X into phi Y belongs to H bar, and phi is a homomorphism. You see, phi is homomorphism. So therefore we shall use the property, multiplicative property of homomorphism. That means this phi X into phi Y is same as phi of X into Y, and this belongs to H bar since phi is a homomorphism. Phi is homomorphism, and see phi of xy belongs to H bar means by definition of H, if phi image of X is in H bar, X is in H. So this implies xy is in H. xy belongs to H, and thus this proves the closure property. X and Y are two elements in H, their product is also in H, and therefore H is closed. We have to prove the properties for subgroup. Now the next property we have to prove is existence of inverse. So inverse exists for every element in H, that we shall prove. And so for that purpose, suppose an element in H and show its inverse is also again in H. So inverse, existence of inverse. Let X belongs to H. So what this implies by definition of H, if X is in H, phi of X is in H bar. Every element of H is having image in H bar under phi. So therefore X belongs to H, its phi image is in H bar. And again you see H bar is subgroup. H bar is subgroup of G bar. So therefore its inverse must exist. This implies inverse of phi X belongs to H bar since H bar is subgroup of G bar. Therefore it contains the inverse of for every element. And again by the property of homomorphism, phi X inverse of phi of X is same as phi of inverse of X, and this belongs to H bar. Since we have proved this earlier, inverse of phi X is equal to phi of inverse of X, and thus phi of inverse of X belongs to H bar. And again this implies if that belongs to H bar, this X inverse must belongs to H by definition of H. So this implies X inverse belongs to H. So this is by definition of H. And thus if X belongs to H, we have inverse of x also belongs to H. That means inverse exists for every element. Every element of H. And thus this shows that H is subgroup of G because it is closed and every element in H has inverse in H itself, and therefore H is a subgroup of G. Thus H is a subgroup of G. So we have proved these two results. H is subgroup of G and H contains K that we have proved earlier. Now the next part is if H bar is normal in G bar, then H is also normal in G. So the lemma established the relation between the subgroups. And if H bar is normal in G bar, then its inverse image of H bar is H. Under this homomorphism, that is also normal in G, that we have to prove. Now further, let H bar be normal in G bar. We shall prove H is normal in G. And for that purpose, what we have to consider by definition of normal subgroup, we shall suppose H belongs to H, G belongs to G, and then we have to prove that GH inverse of G also belongs to H. Let G belongs to G, H belongs to H. So this implies phi of G belongs to G bar and phi of H belongs to H bar. See, G is in G, its phi image is in G bar, and H is in H, its phi image is in H bar. And because H bar is normal in G bar, we have this implies phi of G by definition of normal subgroup, phi G or phi of G into phi of H into phi of G inverse of phi of G. This belongs to H bar, since H bar is normal in G bar. We have used the condition for our definition of normal subgroup. So this is in G bar, this is in H bar. The product phi of G, phi of H, inverse of phi of G also belongs to H bar. This is the reason H bar is normal in G bar. But now we can use the property of homomorphism, multiplicative property of homomorphism. What that implies is phi of GH inverse of G. GH G inverse belongs to H bar. The reason for this is phi is homomorphism. Therefore, multiplicative property holds. And again, this phi of this element GH G inverse belongs to H bar by definition of H. So this is in H bar, its inverse image must be in H. Means GH G inverse must belongs to H. So this implies this is by definition of H, and thus this shows that H is normal in G. What we have written, G belongs to G, H belongs to G, and the product GH G inverse belongs to H, and this shows that H is normal in G. And this happens for all G belongs to G, H belongs to H. Hence, or thus, H is normal in G. So that we have shown whenever h bar is normal in g bar, then h is normal in g. Now it is given phi is homomorphism between g and g bar. Further, or next, we see we have phi from g to g bar is onto homomorphism. And we have just shown h is subgroup of g and h bar is subgroup of g bar. H subset of g and h bar subset of g bar. Therefore, we can consider this mapping between h and h bar, that is phi mapping from h to h bar, and that is also an onto homomorphism, because whenever h bar is normal in g bar, then h is normal in g, that we have proved. So therefore phi from h to h bar is also an onto homomorphism. So we have a homomorphism or onto homomorphism between h and h bar. Whenever we have considered first here h bar as a normal subgroup of g bar, or h bar is normal in g bar, then h is normal in g. That its inverse image we have considered. Now we consider the converse part. Conversely, suppose L is a subgroup of G. Conversely, suppose L is a subgroup. Now first we shall consider a subgroup in this, and then we shall define L bar, that is image of the elements of L, and let L bar is equal to x bar belongs to G bar, such that x bar is equal to phi of L. L belongs to L. So this is the name. Instead of now the name is changed. Instead of H, we are considering L. L is in G, and that is a subgroup. And we have, for every L belongs to L, its image phi of L is x bar, or this is x bar, and that belongs to L bar, or this x bar is phi of L. So this is the definition of L bar. And now we shall say in the similar way, whenever L is subgroup of G, L bar is also a subgroup of G bar. Then L bar is a subgroup of G bar. Now it is easy to verify how it becomes a subgroup of G bar. Closure property is satisfied, and it is non-empty, because the element L is subgroup means E is certainly there, identity element, and its image is E bar, that is in L bar by definition of L bar, and therefore it is non-empty. And closure property can be verified as if two elements are considered, x bar and y bar, then they will have its inverse image in L. And because phi is homomorphism, as in the earlier case, see, suppose x bar, y bar belongs to L bar, this will imply x bar is equal to phi of L1 and y bar is equal to phi of L2. So what will be for L1 L2 belongs to L, and what will be x bar into y bar, that will be phi of L1 phi of L2. We shall only verify, not necessary to write in the proof, or this is a it is similar to the earlier part. And that phi of L1 into phi of L2, or this implies x bar into y bar is equal to phi of L1 L2, and L1 L2 belongs to L because L is subgroup, and therefore this belongs to L bar by definition, and this implies x bar y bar also belongs to L bar, closure property. Likewise, we can see inverse. If x bar belongs to L bar, this implies x bar is equal to phi of L. And what will be the inverse of this? X bar inverse. So that will be inverse of phi L. And inverse of phi L will be, by definition, it is phi of L inverse. Because phi is homomorphism, and phi of L inverse belongs to L bar, and this shows existence of inverse, and therefore L bar is subgroup of G bar. Now what we want to further show, that suppose T is another group, another set. Let T is equal to Y belongs to G such that phi of Y belongs to L bar. Then that means T is the set of all elements in G whose image, phi image, is in L bar. Now we want to show T is same as L, or this is what we want to show, L is equal to T, and that means the inverse image of L bar is exactly L. So this is what we want to show. For that purpose, we shall show L is subgroup of L is subset of T, and also T is subset of L. Now first part is L is subset of T. If, or you can say, L belongs to L. So what this implies, if L is in L, then phi of L is in L bar, or it is x bar, and x bar is in L bar. So this implies phi of L belongs to L bar. And again, if phi of x belongs to, phi of L belongs to L bar, phi of y belongs to L bar, then y belongs to T, and this implies this L satisfies this condition, so therefore L must be in T. So this implies L belongs to T by definition of T, because T we have defined, that is Y, those elements in G whose phi image is in L bar, and phi image of L is in L bar means L must be in T, and thus this shows that L is subset of T. Next, let T belongs to T. We will show the other part, that is T is also subset of L, and let T belongs to T. So this implies, now if T is an element of T, then this phi image, its phi image must be in L bar. So its phi image, that is phi T, belongs to L bar, and this further implies phi of T. So what are the elements of L bar? The elements of L bar are having the phi image of L, elements in L. So therefore this phi T is in L bar, means this phi T must be equal to some phi L. So this implies phi T is equal to phi L, or some L belongs to L by definition of L, or some L belongs to L, because the elements in L bar are having this phi of L, for L belongs to L. So that same thing we have written here, phi T is equal to phi L, and further we shall multiply or post multiply both sides by inverse of phi L, and thus this will be phi L into inverse of phi L, and this implies, see, by property of homomorphism, phi T into phi of or Before that, we can write this as phi of t into phi of L inverse, and this is identity element of G bar, and that is A bar. So this we have written. Further, this implies, I shall write above, or we have used this and I shall continue here. So this implies phi of t into L inverse is equal to E bar. And what this further implies, phi image of this element is E bar, means this element must be in the kernel by definition of kernel, because kernel contains those elements whose image is identity. And so this implies, see, t into L inverse belongs to kernel K, and this kernel K is a subset of L, because L is subgroup, and this is K is subset of L, since L is a subgroup. Therefore, it contains K. K is subset of L, and thus this implies T into inverse of L belongs to L, or that further implies T belongs to L into L. Multiply both sides by L. But L into L, L is in L, and therefore, see, L is in L, and therefore L into L is again L by closure property. And this implies T belongs to L. Since L belongs to L, implies L into L is equal to L. And thus, starting with T belongs to capital T, we have T belongs to L. And that means this T is subset of L. So therefore, T is contained in L. And thus we have proved both part, L is subset of T and T is subset of L. Hence, we have both T and L are equal. Hence, T is equal to L. And thus, this set are the same. And that means this is one-to-one correspondence between subgroups of G bar and subgroup of G. So that is what we wanted to prove. This association sets up a one-to-one mapping from the set of all subgroups of G bar onto the set of all subgroups of G, and which contains K. So thus this proves the lemma. Thus there is a one-to-one correspondence. One-to-one correspondence means one-one and onto mapping. Between the subgroups of G bar and the set between the set of all subgroups. Set of all subgroups of G bar and the set of all subgroups of G. Which contains K. K is a subset of this subgroup. And further, also we have proved that if these subgroups, this correspondence has a relation, normal subgroup of G bar is mapped to normal subgroup of G. A normal subgroup is having image as normal subgroup of G bar. Also, Also, a normal subgroup of G bar corresponds or has inverse image, has its inverse image as a normal subgroup of G. So thus in this lemma we have proved if phi is homomorphism from group G to group G bar, then and if this homomorphism is onto, then there is a one-to-one correspondence, or that means 1-1 and onto mapping between the subgroups of G bar and the subgroups of G, and that mapping also corresponding to normal subgroup of G bar and normal subgroups of G. So this proves the lemma. So thus we have proved the lemma, and the remaining part we will continue in the next lecture. Thank you.